Hi, I am Natakorn Intranukul. In this video, I'm going to talk about the compressed air engine. What is a compressed air engine? Compressed air engine is a pneumatic motor that does mechanical work by expanding compressed air. The core concept, unlike the internal combustion engines that rely on the ignition of the fuel to create pressure, a CAE relies on the release of the pre-compressed air from a high-pressure storage tank. There are two primary components. The first one is the pressure regulators. The second one is the piston or the rotary engine mechanisms driven by gas expansion. High-pressure carbon fiber or steel storage tank, often storing air at around 4,500 psi or around 300 bar or higher. How does it work? There's four different mechanisms. The first one, air is stored at extremely high pressure. Two, it is fed through a regulator to lower the pressure to a usable level. Three, the air enters the engine cylinder where it expands. Four, the expanding air forces the piston downward or turns a turbine, creating mechanical torque. The thermodynamic challenge. According to the ideal gas law, or the PV equals to nRT, expanding a gas causes its temperature to drop without drawing heat from the environment. The engine can freeze up, or we can say that it is a diabatic expansion. Advanced CAEs use heat exchangers to draw ambient heat into the air before or during the expansion. The anatomy of the high pressure storage. The container, storing air at 300 to 450 bar, which is around 5,000 psi, requires highly specialized vessels. Standard steel tanks are far too heavy for vehicle applications. The modern materials. Advanced compressed air vehicles utilize Type 4 cylinders, a high-density polymer linear, fully wrapped in aerospace-grade carbon fiber. Safety mechanics. Unlike the combustible liquid fuels or highly reactive lithium-ion batteries, compressed air is inert. In the event of a severe collision, carbon fiber tanks are designed to rupture and vent the air rapidly, but harmlessly, avoiding the shrapnel explosion associated with the traditional metal tanks. Historical context and early uses. This is not a new concept. The pneumatic system has been used since the 19th century. For example, mining locomotives from the late 1800s to early 1900s, extensively used in coal mines. Because CAEs produce no exhaust gases, sparks, or heat, they completely eliminated the risk of igniting explosive methane gas or coal dust. The naval torpedoes. The Whitehead torpedo in 1866 used a high-pressure compressed air engine to drive its propellers. Paris tramway in 1870s, operating using Mekursky system, which preheated compressed air with steam to prevent freezing. The advantages of the compressed air vehicles. The first one is the zero tailpipe emissions. The only exhaust is clean, cold air. 2. There is no toxic battery materials, unlike the EVs that require lithium, cobalt, and nickel. CAVs use primarily aluminum, steel, or carbon fiber for tanks. Rapid refilling. Refilling a compressed air tank takes only a few minutes, comparable to pumping gasoline, whereas EV batteries require significantly longer charge times. Long cycle life. High-pressure tanks can be refilled tens of thousands of times without degradation, seen in chemical batteries. The thermodynamic bottleneck, or the disadvantages. The low energy the low energy density. Compressed air at 300 bar holds only about 0.1 megajoule per liter. For comparison, gasoline holds about 34 megajoule per liter, and lithium-ion batteries hold about 1 to 2.5 megajoule per liter. This results in severely limited driving range. Poor well-to-wheel efficiency. Compressing air generates massive amounts of heat. Generally energy lost to the environment. Expanding air absorbs heat, meaning the engine runs cold and loses efficiency unless heated. The result? The overall energy efficiency of a CAV from the power plant to the wheels is estimated at 5% to 7%, compared to 70% to 80% for the battery electrical vehicles. Technology comparison metric. This table shows you a quick look at how compressed air compares to the standard ICE and the EVs. Fuel energy density. ICE very high, around 34 megajoule per liter. EVs moderate, around 1 to 2.5 megajoule per liter. CAE very low, around 0.1 megajoule per liter. Well-to-wheel efficiency, ICE 15% to 20%. EVs 70% to 80%. Compressed air engine 5% to 7%. Refilling time, ICE 3 to 5 minutes. EVs 30 plus minutes for a fast charge. CAE 2 to 5 minutes. Tailpipe emissions. ICE high CO2 and NOx particulates. EV 0. CAE 0 because it is a cold air. End of life impact. The ICE moderate. Recyclable metals. EVs very high complex battery recycling. CAE low very easily recyclable materials. Modern developments and the future. Notable attempts. Companies like Motor Development International and Tata Motors have prototyped air cars for low-speed urban environments. Hybrid pneumatic engines. Researchers are investigating hybrid systems where an ICE uses compressed air for starting or recovering braking energy, improving overall fuel efficiency. Grid energy storage. While inefficient for cars, compressed air is highly valuable for stationary grid storage. Excess renewable energy compresses air into underground caverns, releasing it to spin turbines during peak demand. To conclude, while mechanically simple and environmentally clean at the tailpipe, compressed air engines in transportation are fundamentally limited by the laws of thermodynamics. Their future likely lies on niche urban vehicles, hybrid system, and large-scale um sorry large-scale stationary energy storage rather than replacing EVs. And that is it for this video. Thank you so very much for watching.